Hi, welcome back. I'd like to put into words now the concepts that we've been discussing about a limit. So when we talked about the graphical idea of a limit, we had a graph of a function. We were trying to figure out, well, what should the function value be at a point A? And our goal is to be able to say, well, what does it mean to say that what the function should really be? So let's give a precise, intuitive definition of a limit. We're going to get to a mathematically precise definition in a little bit, but right now we'd like to be able to say, what does it mean for the function to have a limit at a point? So here we are. So we'd like to be able to say the limit as x approaches a of f of x is equal to L. We'd like to say this limit of the function as x approaches a is equal to L if we can make the values of f of x arbitrarily close to L. So if we here at L, and we can say we can ensure that the function values are within a certain distance from L whenever we choose x values that are within a certain distance from A. So what does it mean that it's possible to have a limit? It means that we can make sure that we get close enough to that limiting value as long as we're close enough to A, but not exactly at A. So we're going to ignore those cases when you have, for example, you have a hole here, or you have a jump where you have a point that is landing there. The function is defined at A, but it's just off of the curve. So our goal here is to say we want to force this function value to be close to L by choosing x values that are close to A. So let's get a specific example and talk through how that works for this example. So we're going to consider the function f of x is equal to the cubed root of x. Now this is a function that looks like this, where when you plug in a number, you take the cube root of that number. So when we plug in 1, we get 1 because the cube root of 1 is 1. And when we plug in 8, what number when you cube it is equal to 8? That's equal to 2. So we have this function. This function doesn't have anything crazy happening. The limit of this function we would expect. So we want to be able to say the limit as x goes to 8 of f of x is equal, or of the cube root of x is equal to 2. And so how do we say that using this intuitive definition of the limit? Well, we want to be able to say that when you're close to 8, you give values that are close to 2. So what we're really saying is how close to x equals 8 do we have to be in order to make sure that f of x is very close to 2? What we're saying is we're going to get really, really close to 2. So let's say we're within 0.1 of 2. So what if we're between 1.9 and 2.1? Can we make sure that the function values near 8 stay between 1.9 and 2.1? That's our question. How do we ensure? What window of numbers down here will make sure that we stay between 1.9 and 2.1? Okay, so in order to do that, what we're going to look for is we're going to look for, well, what x value can we put here that's going to give us 1.9? So what number, when you take its cube root, is equal to 1.9? So we want the cubed root of x is equal to 1.9. In order to solve that equation, we cube both sides, and we get that x is equal to 1.9 cubed. A little bit of calculator there gives us that 1.9 cubed is 6.859. So if we plug in, if we look at this point right here, 6.859, and we take the cube root of that number, we get 1.9. Similarly, if we look at 2.1 and we say, well, what value is it that when you take the cube root of that number you get 2.1? The answer is 9.261. Alright, so we know that f of 6.859 is equal to 1.9. We know that f of 9.261 is equal to 2.1. And so if we restrict x to be between 6.859 and 9.261, then f of x is going to land between 1.9 and 2.1. That's our goal. Our goal is to make sure that there's some interval down here in the x-axis where if we stay in there, we know that our function value is going to be close to 2. And it doesn't just have to be between 6.8 and 9.2. It could be between 7.5 and 8.5. If we chose a smaller interval, that would also be the case that the function is between 1.9 and 2.1. Alright, so that's how we can, that's what's happening when we're talking about this limit. We're talking about showing that the function values get really close to L. So let's just look at the two cases that are broken, right? We came up with two good cases where this is not true, right? The first case was when we had a jump. So if we have a jump and we'd like to say, well, maybe this is limit L. Wherever this limit is, well, is there an interval down here where the function values get close enough that where the function values for everything in this interval is really close to L? And it's not true, because all function values always will lie between -1 and 1 for any interval around 0. And so whenever you have a jump discontinuity, whenever you have this jump of this function that goes from one side to the other, this definition isn't going to work, because it's not going to be possible to get within a small distance of the limit. Right? We also had this other example of the sine of 1 over x. Alright, and so if we're here at 0, can we find a value where all of the points lie within that value, where all of the function values for everything in this interval are close enough to our point? And the answer is no, because it's wiggling so much. You're never going to be able to make that small x interval small enough to be able to ensure that the function values will lie somewhere on the y-axis in a particular interval. Okay, so what I'm going to say is that I want to make sure everybody understands this idea of this intuitive definition. what's happening in terms of choosing, what does it mean to say this intuitive definition, and what's happening in this picture here. I want to make sure everybody understands that. And what I'd like everybody to do is also listen to this next part, but you're not going to be tested on it. It's for the general knowledge, because it's a really fascinating idea about, we talked about intuition, but if we want to make this precise, how do we make this precise? So here's the idea about delta epsilon proofs. So if you wanted to show that a limit exists, this is how you would do it. So you would say, so we're going to use two special terms. We're going to use delta, and we're going to use epsilon. Delta represents some small horizontal value, distance, and epsilon represents some vertical distance. The official definition of the limit says, the limit of f of x as x approaches a is equal to L when, for every epsilon, for every small vertical y value, we can find a delta where the distance between f of x and L is less than or equal to epsilon, whenever the distance between x and a is less than delta. So that's a lot, and that's a mouthful. You should read it multiple times to see what it's saying. And if we're going to restate that, what it's saying is, no matter how close you want to make the function value to L, no matter how close you want to put that window on the y-axis, you can always find a window of x values whose function values are that close. So here's, for what we talked about just before this, we claim that this limit as x goes to 8 of f of the cubed root of x is equal to 2. So what that is from this official definition, this function f of x is equal to the cubed root of x, a is equal to 8, and L is equal to 2. So let's take this and translate it into the equation that we had from before. We need to show that for every epsilon, we can find a delta such that the distance between the cubed root of x and 2 is less than epsilon whenever the distance between x and 8 is less than delta. So we already approached this for one particular epsilon. So on the previous page, we had that epsilon was equal to 0.1. And what we showed on the previous page was that we can ensure that the distance between x, the cube root of x, and 2 is less than 0.1. It's less than epsilon whenever x is in this interval. X is between 6.859 and x is and 9.261. And so we know that whenever we're in this range, 6.859 to 9.261, and that's around 8, we know that whenever we're in this range, the function value is between 1.9 and 2.1. And so what we want to show is we want to show that there is some window that's around 8 where everything in that window that's symmetric gives a function value that is between 1.9 and 2.1. So if we look at this distance between 8 and 6.859 is 1.141. And the distance between 8 and 9.261 is 1.261. So we see that the distance from 8 to this right endpoint is bigger than the distance between 8 and this left endpoint. So if we shrink this window so that it is 1.141 on both sides, 1.141 on both sides, then everything in this interval still works. So that's what we said last time. On the last page, we said that even if you restrict to a smaller interval, the function value is still between 1.9 and 2.1. And so, what we've seen is that whenever x, the distance between x and 8 is within 1.141, whenever this distance is less than or equal to 1.141, then the function values, the cube root of x, is within 0.1 of 2. And so what we did is we found that when epsilon is equal to 0.1, then a delta that works in the statement is 1.141. If we would want to prove that this is true, that this limit exists, you would need to be able to show this for every epsilon. You need to be able to figure out what's the right delta for every single epsilon. And so that requires normally some calculations. It's not the most pleasant thing, but it is what you would need to be able to do. You give me an epsilon, figure out what the formula is for delta that allows you to show that the distance between L and F is less than epsilon whenever the distance between x and a is less than delta. There is an appendix of the book if you'd like to learn more. And so what we're going to be talking about next time in class is we're going to be talking about, let's say we had some equations of what the function is, and your goal is to show what the limit is. So we're not going to be using deltas and epsilons to do that. We're going to learn some techniques and some calculations to be able to do that. All right. See you next time. Bye.